In-class activity 4A, modeling the motion of a pendulum. Léon Foucault was a 19th century French physicist who used a very large pendulum to demonstrate the effects of Earth's rotation. A replica of his original pendulum is on display in the Pantheon in Paris, where he first demonstrated his experiments to the public. The pendulum consists of a brass-coated lead sphere suspended from the ceiling using a 67-meter wire. The pendulum is set in motion by moving the sphere to an angle of 0.148 radians and then releasing it. 1. If the pendulum is set in motion by releasing the sphere from an initial angle of 0.2 radians instead of 0.14 radians, would the amplitude of the motion change? Would the period change? Let me just extend the page a little bit there. And the answers are, I'll just write them quickly here. The amplitude of the motion changes. But the period does not. Let's go on to the next page. Objectives for the activity. You will understand that a cosine function can be used to model the oscillations of a pendulum. You will be able to write and graph equations that model the oscillations of a pendulum and identify those parameters that affect the amplitude of a pendulum's motion. In preview assignment 4A, you were given an equation to model the angle of a pendulum as it swings back and forth. The angle theta of t is in radians. Ignoring friction, theta of t is equal to theta sub 0 times cosine of the square root of g over L times t, where theta sub 0 is the initial angle measured in radians of the pendulum just before it is released. G is the acceleration due to Earth's gravity, that's 9.81 meters per second squared. L is the length of the pendulum in meters, and t is the time since releasing the pendulum in seconds. Note, the variable t is not underneath the square root symbol. 2, determine the equation for theta of t that models Foucault's original pendulum. Assume that the initial angle of the pendulum is 0.148 radians. What are the units of theta of t? Well, if we think about this, let's see, we have theta sub 0, that's equal to 0.148. And then we have, let's go this way, L is 67, and that was meters. G, gravity is 9.81, so 0.81 meters per second squared. Now, if we put all this together, let's write theta of t is equal to theta sub 0 times the cosine. Now this is the square root of g over L, and then times t equals, we'll put in the 0.148, and then we have cosine square root 9.81 over 67. That's all in the radican. And then we have t outside the radican. And then continue underneath here, 0.148 cosine. And then we could just write this as 0.383 times t. And our units, they're going to be, the units for theta of t are in radians. And we'll write that here. The units of theta of t are radians. All right, let's go on to part 3, number 3. We know that cosine of t has a period of 2 pi. Therefore, cosine of 0 equals the cosine of 2 pi. Part A, in your formula for theta of t, what value of t will cause you to take the cosine of 2 pi? use this value to determine the period of theta of t. So let's think about this. The value of t that yields an argument of 2 pi is determined by setting 0.383 t equal to 2 pi. Now, if we solve this equation, just we're going to solve it for t, we're going to get that t is equal to, or approximately equal to, because we're going to use 6.28 for 2 pi, and that's over 0.383, and approximately 16.40 seconds. Okay, so this tells us that the period is about 16.4 seconds. Let's go to the next part, part B. Part B, the graph of theta of t is shown. Does the graph support your answer to part A? Explain. Well, let me just move this up a little bit and then slide it back down. And I'm going to put here, yes. It appears that one complete cycle of the pendulum will take about 16 seconds to complete. Okay. One complete cycle. Supposed to be an A pendulum. Take about 16 seconds to complete. So if we think of one cycle, if we start here, let me try a different color in red here. If I start here at 0 and we trace this all the way down and then back up to one cycle, it looks like we're somewhere about 16. So let's go on to, there's a part C. Let me scroll this down a little bit and see what's here for part C. Part C, it says, what is the frequency of the pendulum? That is, how many complete cycles will the pendulum make in 1 second? Well, it's going to be 1 over 16.4, which is approximately 0.061 hertz. Four, suppose that Foucault's pendulum was set in motion by releasing it from an initial angular position of 0.2 radians instead of 0.148 radians. Part A says, without writing any equations, predict how the graph of theta of t will change. Be prepared to share your reasoning. Okay, so the amplitude will increase since the initial angle from which the pendulum is released increases. So the frequency nor the period will not change, since neither depends on the initial angle, theta sub 0. The only values that affect the argument of the cosine function would be g and L, which remain unchanged in this scenario. So, well, let's write some of this down. The amplitude increase since the initial angle from which the pendulum is released increases. The frequency nor period, that's a W, believe it or not, there, will not change. Since neither depends on the initial angle. And the initial angle is theta sub 0. The only values that affect the arguments of the cosine function would be G and capital L. Let's go to part B. So that's 4A. This is part B for 4. It says write the equation for theta of t for the case in which the initial angular position of the pendulum is 0.2 radians. Well, we could do this. Theta of t is equal to 0.2 times the cosine of 0.383 times t. Part C. What is the period of this pendulum? Well, since the period does not depend on the initial angle, it's the same as that of the first case, approximately 16.4 seconds. So it's about 16.4 seconds. Part D. Sketch theta of t on the same set of axes as your graph from question 3, part B. Okay. So here we go. That's the same graph that we saw back a few screens ago. And to sketch this, let me just do it in another color. How about green? We're going to sketch this, and the amplitude, let's see, is going to be 2. And it's going to cut through the axes at the same points, but it's going to go down a little bit farther and up a little bit farther. So I'm going to go like that. I'm just going to draw a little bit of this to get started. So it's going to come down here, cut through the axis, go all the way down to the negative 0.2, and then turn around, go back up, cut through the axis at the same place the other curve did, and then reach our max at 0.2. And I'm just going to keep following this curve all the way until we're done. It's supposed to reach the bottom there. It turns around, goes back up, max, and I'm in down here. Whoops, there we go. And that I want to just erase a little bit, and I can do a better job than that. All right, so that's what it looks like in green there, as compared to the first curve that was sketched for us. Let's go to the next screen. And is it part 5? Yep, part 5. Part 5, it says, take note of some of the similarities and differences in the equations and graphs for the 2 cases mentioned so far. Be prepared to explain the reasons for these similarities and differences. Okay, so we have a couple of equations here. So our equations, let's call them case 1 and case 2. So for case 1, we had theta of t is equal to 0.148, and then times the cosine of 0.383t, close the parenthesis. And then let's do case 2 right under that. Here we have theta of t is equal to 0.2, again, times the cosine 0.383 times t. The equations, you can see here just by writing them that like this, that the equations have different amplitudes, but both have the same frequency and period. The graphs, since the frequency for both cases is the same, it means that the graphs will intersect the horizontal axis at the same points, which we saw. Also, the maximum and minimum points will occur at the same time, and the graphs have a similar shape, but are scaled differently due to the differences in their amplitudes. The one had an amplitude of 0.148, and the other had an amplitude of 0.2. So let's go to part 6 here, number 6. It says a student constructs his own pendulum, sets it in motion, collects data, and graphs the corresponding function theta of t. Given the following graph, determine the formula for theta of t. So let me just extend the page a little bit and then move it up like this. And we could say that says let me write a better word than that. How about, there we go. The period appears to be 2 pi. The amplitude is 0.05. So what we get here is theta of t is equal to 0.05 times the cosine of t. And that is the end of this video. Thank you.